Hi, my name is Scott Simpson, and today we'll be talking about mechanisms from a PChem standpoint. This is not similar, it is related to mechanisms from an organic chemistry standpoint. However, we're not going to be drawing arrows. We're going to be talking about elementary reactions. And what a mechanism is it's a sequence of reactions that lead to some overall chemical change. So, mechanism. The sequence of elementary reactions that lead to an overall chemical change. Mechanisms are often used to explain these changes. However, you can't ever truly prove that a mechanism exists. You can disprove mechanisms, though. So, cannot be proven. Correct. The reason for that is we'd have to be able to isolate a transition state, but we can only prove them wrong. That might change in the future if we have a way to measure those transition states. However, I use this term elementary reactions. Next, we're going to talk about what are elementary reactions. When it comes to elementary reactions, these are the simplest form of reactions that cannot be broken down into simpler steps. In the past, I said the rate law has to be determined experimentally. It is not related to the stoichiometry. However, if the rate is dependent on an elementary reaction, you can utilize that stoichiometry. So, rate of the step, or that elementary reaction, is determined by stoichiometry. It's determined by molecularity rather than order. In each of an elementary steps, there's only a single transition state and there are no intermediates. The other thing is when you take all of the elementary reactions and you sum them up, they should equal the overall rate law. Sum of elementary steps should result in the overall rate law. And most of the times with these elementary steps, what they're comprised of is the decomposition / dissociation of a molecule or two entities coming together to form a new product or a new molecule. So let's look at an example of this. So example, determine the rate law, the rate expression for the following elementary steps. Then we'll just do this other one. Okay, so since we're told that they're elementary steps, that's the biggest thing. Always look to see if you were told they're elementary steps or if it's implied that they're elementary steps. Then we can determine the rate law. So we have the rate is equal to, we're going to have some rate constant times, in this case, we care about the reactance, and 204 gas raised to the power of 1. For this next one, again, given it's an elementary reaction, we can have the generic form rate is equal to K, the rate constant, times we have our first product, NO2, raised to the power of 2 because that stoichiometric coefficient is there, and then O2. Pretty simple. Okay, elementary steps that involve 3 or more reactants tend to be pretty rare. They do happen, but it is rare. Okay, let's look at an example where we consider an overall reaction. We break that overall reaction into individual elementary steps, and we consider what would the rate laws look like depending on the speed of those elementary reactions. Okay, so consider the following reaction. ICl plus H2 goes to I2 plus 2HCl. And I'm going to tell you the overall rate law is rate is equal to K sub R, concentration of ICl times H2 gas. We're going to ask, what is the mechanism? Given the following information. And then we also have HI plus I, the rate constant of K2, K sub 2, okay, this is going to be step 1. This is going to be step 2. And in terms of the reaction speeds, that one's slow, this one is fast. So the bottom second step is fast. Okay, let's look at some information with this. First, let's see what happens when we slap these two elementary steps together. So if we put those two steps together, get ICl plus H2 plus HI plus ICl goes to HI, HCl, HCl plus I2. Okay, there's going to be some things that cancel out. Anything that appears on both the left and the right. So our HI is gone. This is going to be a reaction intermediate. It is around while the reaction is occurring, but generally it gets consumed or produced at an equal rate, gets gobbled up. Okay, so when we write everything over, let's combine like terms. We end up with this, which matches our reaction. So we can be we can propose that this is a mechanism because when we slap these two things together, we get that as an overall thing. Okay, so let's ask a couple questions. So first question, which step dictates the rate? So of these two steps, which one's controlling the rate? The answer to that one is the top one, because it's slower. What happens is you slog through this step, and this step happens quickly. So the rate is actually determined by the slowest step. Might have heard the term, you're only as fast as the slowest buffalo, or if you have a herd of buffalo, the herd moves along with the slowest buffalo. Same sort of thing happens with reaction mechanisms. So the answer to this is step one. Okay, so let's consider what the rate would be based upon step one as an elementary step. We have rate is equal to K1, concentration of ICl, concentration of H2. And hey, if we explore this, look, these two match. So that provides evidence that the mechanism that we have proposed is correct. Now, let's look at a different scenario. How would this change, or how would our rate law change? Let's say instead of this one being the slow step, step one, we switch step two to being the slow step. So let's try and answer that. So here, we're going to switch the speeds. This one, step one, is now fast, and step two is slow. So question, we're going to ask, question. How would the rate law look if step two were slower? Okay. So, in order to define that, we know that the rate would be dependent on step two because it's the slower step. And since it's an elementary reaction, we can say that this is true. However, there's an issue with defining the rate law based upon this. If you look, HI, that's an intermediate. So we really don't want to define a rate law based upon an intermediate. So we're going to have to look at another way to define this. Okay, so let's consider where HI is being produced. HI is only being produced in this reaction, and then it's being consumed here. So it's being gobbled up in that second step. However, what controls the concentration of HI? Well, if we consider the concentration of HI, that is completely dependent on this first step. We'd have K1, ICl coming together with the H2. So what we would do next is we would take that and plug it in here, and what we would end up with is an overall rate law. We'd have K2 times K1, concentration of ICl, concentration of H2, times ICl. Okay, now, if you look, we have two constants that are going to be multiplied together. A lot of times you'll find that people like to keep those constants so they can talk about their mechanism and see how it works out. So this might be expressed, I like to put them in order, K1 times K2 ICl squared H2. And what you could say is you could slap these two constants together, and let's call that one k prime. So if the second step were the rate determining step, and in terms of the speeds, if they were switched, this is what the overall rate law would look like. Okay. So in this video, we talked about mechanisms from a PChem standpoint, how to come up with those different mechanisms, what an elementary step is, and how, when you add all of these things together, how do you get the overall rate law? Thank you for watching, and please leave any questions or comments below. Thank you.